Lagos, Nigeria, and he's going to be talking about parallelizing the internal stages and high-order two-derivative DIRK methods with applications.
Thank you very much for the introduction. And my name is Julius, and I work at the University of Lagos. And my research all along has been on numerical methods for differential equations, ordinary differential equations, not partial differential equations. And I believe that you might find some methods that may be useful for your research, because when I saw this workshop, I tried to apply because I've always been following the Parallel in Time community. The first one that I attended was the one that was organized by Felix in a virtual, it was a virtual meeting at that time. And I've also attended some workshop Professor Martin also some talk about parallel in time, and I've always followed the community. And the reason for me not working in the area of PDEs and parallel in time is because we don't have the resources and computational resources to actually do this thing. But I've been following the community and the research in the but my research is on ordinary differential equations, and I try to just give some methods that I've been working on. And also, because of this meeting, I try to see how I can put some kind of parallelism into what I do, which I don't really do normally, but just because of this meeting, I try to do something. Okay, so my overview of my presentation would be as listed. So I'll be talking about some motivation, the model problem, construction, the linear stability analysis. And I'll give some numerical experiments, and also to now introduce the parallel architecture that I framed into this topic. Oscillatory differential equations evolve in many of these class of problems in celestial mechanics, in molecular dynamics, quantum chemistry, and in genetic regulatory systems, to mention a few. And we can see in this kind of acoustic wave equations, you can see some kind of dynamics that are oscillatory. And a very important problem that is considered is the Fermi-Pascal-Ulam single equation, which the dynamics is kind of oscillatory, and this is a very important problem in the area of oscillatory dynamics. And several researchers have tried to get solutions of this. And you can see from the slides down, you can see that for very large step size, they cannot recover the dynamics of the system. But when they reduce the step size, you can see that they can now recover the dynamics of the system. And these are for even longitudinal method of order 4, they could not give a very good, a very good presentation of the dynamics when the step size is decreased. And ON has also tried to also give the dynamics, also worked on this. So what we look at is the model problem. So we look at ordinary differential equation, the model problem, which is y prime equal to f of y, which we all know. And this has been discussed in this book by Ira. I heard Martin talk about Ira yesterday as his colleague, and he has been one of the proponents of the researchers in the area of numerical methods for ordinary differential equations. And we get to read his books that he has written. And we know that most of these problems that we have some kind of oscillations and non-linearity and stiffness, which restricts the use of large step size. So we need special methods to actually capture the dynamics of these kind of systems. So I just run through the overview of the kind of methods, how methods have been coming. So we look at the DIRK methods, then we look at longitudinal methods with higher order derivatives, because that is the class of methods I'm trying to introduce. Then we look at the two-derivative longitudinal methods, the exponentially fitted longitudinal methods, now the exponentially fitted two-derivative methods. So these are the people that have been working on these areas and the progression over the years. Now, the new way of writing this method is, instead of the F that we are used to in the RK method, we now see that the F is now outside and we have a G, where the G becomes like the second derivative of the model problem. So if we can compute the Jacobian of the model problem, then we can have the second derivative and we can now begin to, integrate our problem from there. This method can also be written in a Pocher stably. So for some of you that are working in the area of PDEs, I heard so many people talk about the backward Euler and talking about, ARK3. So these are some of the methods you can also try to incorporate into this research and see if things are working. Because we've discovered that for stage 1 and 2 of these methods, you can actually get an order of 2s plus 1. So for stage 1, you can get order 3. So I believe you can optimize some of your methods. So the method I'm going to be working on is actually this exponentially fitted two-derivative Ronchi methods. And it's a kind of a modified method to the actual two-derivative method, where we introduced some new parameters psi, and we expect that the coefficients of the RK method are functions of the frequency of the problem and the step size. And these methods are known to work for oscillatory problems because we know the oscillatory problems are problems, maybe for example, problems that the solution comprises of cos and sine. So we kind of adapt that into the numerical method so that it can, get the actual dynamics of the system. And of course, the way to derive these methods is to, get the Taylor series expansion of the exact solution and Taylor series expansion and the Taylor series expansion of the numerical methods and try to compare them up to some certain order or accuracy. And we can now get the other conditions to be able to get these coefficients. And I'm sorry, this is so tiny, but of course you can get this in the reference paper, which I'll write there. But this is the other conditions that we're able to get from this. And these other conditions, well, we had to get a new a new rooted trees for this, because the rooted tree theory, the actual rooted tree theory by Bocher could not capture this. So we had to get like a bicolored rooted tree. And it's just like the one similar to the book of Ira. And we also were able to prove this theorem to give the exponential fitting conditions for methods that has, so the one I put here is just one for the one that satisfies the one for exponential I omega x, but we can do that for several other subspace. And this method we have here is a family of two-stage method, which is of order 4, a two-stage of order 4. For the actual Ronchi method, the family of two-stage method, the two-stage method you can get of order 4 is the method with the Gaussian node, and it's fully implicit method. But in this case, we have a DIRK, which is better in terms of implementation, because for us to do the two-stage method, the two-stage fully implicit method, we have to look at a very large system of nonlinear equations that we want to solve. But in this case, we can split them into the stages and just do the. So, and we found out interestingly that if we choose the parameters in this last line, if we choose these parameters for the C1, C2, and the phi, we get an optimal stage for the 5. And also, this is a 3-stage method of order 6. And we had to do the linear stability analysis and the phase analysis just to help us to choose some method, because we had to optimize some of these methods to know, so that we can actually show how we could optimize this method with some other with some optimized method with the dispersion and the dissipation error. And we found out that if we make phi to be 11/20, you can actually cancel that. You can actually cancel to have a dispersion error for that 7. And if we cancel the second one and make the second one to be 3/40, we can actually have a dispersion error of order 7-2. So we chose those two constants against choosing some other constants for our numerical experiment, just to show the advantage of the optimization. And this is the imaginary stability region of those methods. So all the methods that we have chosen. And of course, another important problem is to look at in this case is the choosing of how to know the frequency of a problem. So there are some authors that have looked at giving some techniques of how to look at the frequency of a system, but we are choosing the one of Ramos and Vigo Aguai. And we actually use this to estimate the error of the Kepler's problem, and we found out the error to be omega to be equal to 5. Just to use slide just to show that we can actually estimate the frequency if we don't have the frequency. Because one of the questions that will arise would be if the coefficients are a function of the frequency and h. How do you know the frequency? The frequency is not given. So you can actually find it. You can estimate it if you don't have it. But for some problems, we know the frequency. So if you choose the frequency, then definitely it will conform with the dynamics of the system. But if you don't have it, you can actually estimate this frequency. And this frequency, the actual technique they used was the golden section technique, which is given by this equation that you have there. Okay, so we go to some numerical experiments now. And so these are the class of methods we are going to be comparing with our methods. So for the methods of order 4, we're going to compare them with these methods listed here. And the last 4 there are the new methods that we got. So the last 2 methods are the optimized scheme that were optimized based on the dispersion error, while these last 2 are the one where we did not optimize, we just chose 0. Okay, and for the 5th order and 6th order, we combined the numerical experiments together, and the last one is our method, while the 4th one is also our method. But the 4th one is a method of order 5, 2-stage of order 5. And for the perturbed Kepler problem, which we talked about, this is the problem. So we converted this problem to a set of ordinary differential equations. And this is the result of the problem. And you can see that the optimized methods, these 2 optimized methods, perform better than the 2 that were not optimized. And they were the best there. And in terms of the computational time, they are more efficient than the other methods. And also, for the methods of order 5, order 5 and 6, the 6th method that we derived was the best method there. And this is our 2-stage of order 5. And in terms of the computational, in terms of CPU time, those 2 methods were the fastest. And we try to make sure that they have the same threshold of error in comparing the efficiency, which is 10. And for the Fermi-Pascal-Lamb problem, we also tried to do that, and we found that those 2 optimized methods also did better than the ones that were not optimized. And we also tried to solve a partial differential equation. And of course, we know that we can do a semi-discretization of the partial differential equation to transform them to ordinary differential equations. And we tried to do that using the central difference. And we transformed them to a differential equation, this form. And we also solved this problem. And we also have this result. Okay, so in trying to now, go into the parallel, into the parallel thing. So I try to see how I can, adapt that method and incorporate some kind of parallelism into it. So what I did was, because I don't work I've not written the code for this, but I'm just looking at if I can, for you to implement a RK scheme, you need to compute the first internal stage to the second internal stage and the third internal stage is serially like that. But can there be a way where we can compute the internal stages at once and now transfer all the solutions into the update? So that will be possible if I just put a 0 here. So in the second stage, I don't need to wait for the first stage. So the first stage computes, second stage computes, and come into the update. And with that, I was able to get this method. So if I have this, then I can compute the first stage and the second stage and put it into the update, and I have my method. So I also did this for the 3 stage. So if I have 3 processors, so I can also do that. So I compute the first stage, compute the second stage, and compute the third stage with 3 different processors. Put all of them in the update. These are the coefficients. And I'm trying for this. I'm not done with this yet because I've not gotten the actual value for C1 and C2. Sorry, for C1, because I need C1 to get C2. But for this, I have a 2-stage and 2 processors. So if I compute the first stage, so I compute this first, compute this on another processor, and I put the results of this one, Y1 and Y2, into these two guys, these two. And it becomes like a 2-stage with 2 processors. And it's possible for me to get a method of order 5 too. And in trying to now generalize that and put it in a very good architecture and something formal, and so we can write the structure for the 2 derivative in this longitudinal expression. And we can also reflect that in the Butcher's tableau. That looks like this. Although this A guy becomes something like this. And in fact, I also learned that if I want this to be more efficient from some of the talks I've listened to today, I can just make these guys down from 831 down to this guy to be zeros. And it will become more efficient because I will have lesser things to compute and I can have something nice to do. And this is going to be like the responsibility of each of the processors. The processors just have to do this and everything just transforms back into the update. And to conclude, I hope I did well. And to conclude, I presented a class of exponentially fitted DIRK method. And for a 2-stage method, we obtain a supercompiler scheme of order P equal to 2s and P is equal to 2s plus 1. And with S equal to 3 stage, we obtain a method of P equal to 2s. And the 2-stage methods were optimized based on the phase analysis. And we also introduced the parallel architecture for the implementation of the method. Our future work will be to derive higher order methods and to write the codes and apply them to more problems. Thank you very much.